All right, next we have Priscila Silva, who is a graduate research assistant at the University of Massachusetts at Dartmouth.
Good afternoon. I'm Priscila. I'm a PhD student. This is my third year. I'm going to present a regression and time series mixture approach to predict system resilience. I have a lot of co-authors. I'm not going to say the names, but my advisor is Dr. Lance Fiondella. So system resilience is the ability to recover from failures. And if critical technologies, if they don't have that ability, what could happen? Military and DoD operations could be disrupted, for example, could cause problems to supply chain and even cause damage to human lives. So researchers have been trying to measure resilience using some metrics, for example, area under the curve, area above the curve. But those metrics, usually it's done after disruptions happen. So it's not very useful, I would say, because sometimes some systems don't have a second chance. So we should be able to track right now what is happening and measure the performance of that system. So for that case, in my PhD, I'm trying to develop some mathematical models that can track and predict performance of systems in future. So here we have a conceptual curve of resilience. So the ability of recovering from failures is actually divided between 4 different states. So a system should be prepared for a disruption, should be able to absorb that degradation to keep the most important service alive. Then it should be able to recover to a high level of performance and then adapt to the new environment. It could be even better than before, or maybe the same, or a little bit lower, but it's still a high level of performance. The problem is, in reality, the system usually have multiple disruptions. It's not just a single one. So we should be able to track those disruptions and recovery as well. So to plot this curve, we are using something that is called the performance, which I'm calling here the P of I. So it's the performance of a system at time step I. And the performance is domain dependent. So we need to define what kind of performance we are measuring. And we say that the performance at time step I is equal to the performance of time step I minus 1, the previous step, plus delta P, which is the change in performance. And what I'm actually trying to track during my PhD is this delta P, how it's changing the performance. So I'm going to present 3 different approaches. 2 of them, it's well-known statistical models using regression models, and the other one is time series models. So regression, I don't have time to explain details here, but regression models, it's very basic. It's just predicting the delta P at time I using covariates. We call them covariates, but it's just basically factors that is impacting the performance of systems. Can be disruptive factors or restorative factors as well. So we need to identify those and plug in our regression equation and then predict the P at time step I. So it's pretty basic, and I'm considering 3 types of regression. It's multiple linear regression with interaction between covariates, and polynomial regression as well. And time series models are kind of similar. However, instead of using covariates in the present time step, we use covariates and performance in the previous steps to predict the step Y, the current step right now. So what I'm actually proposing here is the mixture approach. We are actually mixing it up, regression and time series. We are using covariates and performance in previous interval and in the current interval as well. So it becomes a little larger, the equation. I'm just showing one of them here. And I'm mixing with the 3 types of regression with 2 types of time series models. So it's giving me 6 different mixture models here. So in total, we have 11, which I'm going to test, and we're going to see some results. So we can see that we have many parameters to estimate here, a lot of betas. And so what we should do to apply those models? So first, we need to identify those factors, the disruptive and the restorative factors, which are the x's in my equations. I think that is the most challenging thing to do, identify those factors. It's very hard. And then after we identify them, we need to collect the data. It doesn't matter if you know the performance of the data, but we don't have information about those factors. It's not going to help me much here. So my models are actually very data dependent. I really need a lot of data to perform those models. And after that, we have the data, we have the factors, we have all the data we need. We need to estimate the betas, the parameters of the equation. I'm just using maximum likelihood estimation, but we have many other options here. And then after that, I'm just doing some goodness of fit measures, just seeing how good my models are performing in the actual data. For that, I'm using mean square errors and I-squared, for example. So I'm going to give you an example. I'm not using any engineering data because it's very hard. Like I said, it's very hard to get all the information and factors, unfortunately. So just to demonstrate that it can work, I'm using a finance system. So I'm using a 1980 recession here, but I'm actually trying to predict the number of jobs in the US during the recession. So P, which is my performance, is actually the number of employments that we had in the US on that time. So I'm collecting 8 different factors here. So those are my covariates. They are all statistical indexes. So I just collect the information in the 1980, and I'm using that factors to predict the number of jobs. So to illustrate, like I said, I had 11 different models, 3 from regression, 2 time series, and 6 mixture models. And I'm using different combination of covariates and lags as well of the time series models. To be fair, I'm considering the best set of covariates for each model. So they are not using the same covariates all the models. They have the best set that worked best for the specifically model. So I'm using that combination, and also I'm using 4 different subsets of data. So considering 50, 60, 70, and 80% of the data, just to demonstrate which model could work best for long-term prediction. And after that, I'm evaluating all those models using goodness of fit measures. And then we're going to see some plots to understand better. So I have 4 plots here. It's exactly the same data, the 1980 recession, the number of jobs on that time. So the black line of all graphs here are the actual data, is the number of jobs. It's normalized. That's why you're going to see these numbers over there. And I have the 50, 60, 70, and 80 case over here of the subset of data I'm using. And the dashed vertical line over there, it's just to illustrate where I stopped fitting the model and where I stopped predicting. And the dark gray is the regression model, the light gray line is the time series model, and the blue line is the mixture model. So we can see that for the 80 case, which is the last graph over here in the bottom, we can see that all models performed very well, which makes sense, right? Because we have 80% of the data to fit all the models. So the more data we have, the better the model performs. However, if you go backwards, you're going to see that the blue line, which is the mixture model, it performs better. Even with the 50%, it's not, of course, it's not perfect, but it's better. It can capture better the change in performance. So I'm just picking one right now to demonstrate the measures as well. So the 70% case, we can see that the blue line is very close to the actual data, which is the mixture model. And then we can compare the goodness of fit measures and see that in bold, it's all the best values. So you have the lowest root mean square errors, lowest predictive root mean square errors, and the highest I-squared adjusted. It's just showing that for that case, the mixture model is way better than the others, even though we have 21 parameters in the model. So we can see that I'm using actually 6 covariates there for that model. And for the time series, I'm using 3 covariates. And for regression, I'm using only 2. However, even though the models are being penalized for the number of parameters, I still achieve better results with that model. So now I'm just showing some confidence interval for the same model. For the mixture, we can see there are very few points, maybe 2 or 3, outside the confidence interval over there. So it's giving me a very optimistic result over here. My model is doing pretty well. So that was my talks. That I'm still doing this. This is my 3rd year, like I said. This is my model fit. My next step is actually trying to do some optimal allocation that we can have a threshold for my performance, and then I can actually predict or estimate which factor and how much I should invest in each factor to make our performance improve in a better time. Thank you.